Another type of differential equation is the exact equation, which especially utilizes partial derivatives. Check out how it is computed here in Engineering Math 5. What are exact differential equations? How do we distinguish them from the other forms? Say we have a function z, which is a function of x and y. And from calculus, we have also been introduced with partial derivatives, which use del of the function with respect to x or to y. Now combining them, the derivative of z is dz, and since the function is a combination of x and y, partial derivatives will be used, and through chain rule from multivariable functions, we get the partial derivative of the function with respect to x, dx, and the partial derivative of the same function with respect to y, dy. If we simplify the outcome and denote the partial derivative of the function with respect to x as m and its counterpart on the next term as n, we can simplify the derivative of z as m dx plus n dy. This form is the standard of exact differential equations. Now, in order to make sure that the first order dE with the standard form is truly an exact dE, the test for exactness should be done. TIPE states that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. How was this derived? If we consider a well-behaved function where it is continuous even its derivatives, their mixed partial second derivatives are equal. Mathematically, we can show this statement as the second partial derivative of a function with respect to x and y will be equal to the second partial derivative of the function with respect to y and x. So if we expand each term, we can say the partial derivative of the derivative of a function with respect to x and again with respect to y, and so is the expansion of the second term. And from the previous discussion, we had denoted m for the partial derivative of the function with respect to x and n for that with respect to y. Thus, we can simplify TFE as the partial derivative of m with respect to y, which is equal to the partial derivative of n with respect to x. Here are some examples on how to check a differential equation in TFE. If we have the quantity of x plus 2y times dx plus the quantity of 2x plus y times dy is equal to 0, identify m, which is x plus 2y. Take the partial derivative of the function m with respect to y. Since we are working on the independent variable y, x will be taken as a constant and the derivative of a constant is 0. Then the derivative of 2y with respect to y is 2. So the partial derivative of m with respect to y is 2. Now take the other term and denote it as n. Again, take the partial derivative of n with respect to x this time. And since we are deriving with respect to x, the variable y is considered constant. Thus, the derivative of 2x is 2, but the derivative of y, which is a constant, will be 0. And to simplify, we get the partial derivative of n with respect to x as 2, which is the same as that of the partial derivative of m with respect to y. So we can conclude that the differential equation is an exact dE. Take another example with the differential equation, the quantity of 2xy minus 3x squared times dx plus the quantity of x squared plus 2y times dy is equal to 0. M is taken as 2xy minus 3x squared, and its partial derivative with respect to y is taken as the constant 2x times the derivative of y, which is 1 for the first term, then minus negative 3x squared, which is considered constant at this moment, so the derivative is taken as 0. So the simplified partial derivative of m with respect to y is just 2x. Now the second term is denoted as n. Its partial derivative with respect to x is taken where the first term, x squared, is 2x, and the second term, 2y, will be considered a constant, so its derivative is 0. So the simplified partial derivative of n with respect to y is also 2x, being the same with that of the partial derivative of m with respect to y. So the differential equation is also an exact DE. Moving on, how to find the solution for exact differential equations. We would assume f as the general solution of the exact DE. If we take the general solution of function m, we can get the integral of the function, which would still be the function of x and y, plus the arbitrary constant c1, which is in terms of y. Similar with the case of n, that its general solution will be taken through integration, and the output will be the integrated function of x and y plus a certain constant c2, which is in terms of x. The standard procedure of taking a general solution of exact differential equation is as follows. First, check if the DE is actually an exact DE through TFE, or test for exactness. Next is to determine f from m and n, and this is done through integration, after which add another step to identify c1 and c2. After knowing the constants, the general solution will be identified by taking terms from both f solutions. Here is an example to show you the procedure. We are to determine the general solution of the DE, the quantity of 2x cubed minus xy squared less 2y plus 3 times dx minus the quantity of x squared y plus 2x times dy is equal to 0. First is to check exactness, so identify m as 2x cubed minus xy squared minus 2y plus 3, and its partial derivative with respect to y is also solved. The derivative of 2x cubed with respect to y is 0. The second term will be considered negative x as constant, and the derivative of y squared is 2y. The third term, negative 2y, will be differentiated as negative 2. And the derivative of 3 is 0 as it is a constant. Simplify the solution and we get negative 2xy minus 2. For the next term, we denote n with negative of the quantity x squared y plus 2x. Take note that the sign prior to the function is included. Again, take the partial derivative of n, and this time it is with respect to x. So the first term is negative x squared y, so the derivative of x squared is 2x, and y will remain as y since it is considered as a constant. Then the second term, negative 2x, will be derived as just 2, negative 2. And by simplifying the solution, we get negative 2xy minus 2. These expressions are similar in both derivatives of m and n, thus the differential equation is exact. To start with the general solution, take f by integrating both m and n. Let's work with m first. So f is the integral of the function quantity of 2x cubed minus xy squared minus 2y plus 3 with partial derivative x. The first term 2x cubed will be integrated as 2 times x to the 4th power all over 4. The next term, negative xy squared, will be the constant negative y squared multiplied by the integral of x, which is x squared all over 2. Negative 2y will be integrated as negative 2xy, and the constant 3 is integrated as 3x. Then add the arbitrary constant c1, which is in terms of y. Simplify the solution, which would turn out as f is equal to x to the 4th power all over 2 minus x squared y squared all upon 2 minus 2xy plus 3x plus c1 in terms of y. Now let's do the same integration with the function n, which is the second term of the original dE, and this is with the partial derivative in y. So negative x squared y will keep negative x squared as constant, and the integral of y is y squared all upon 2. Negative 2x will be integrated as negative 2xy. Then add the arbitrary constant in terms of x. So simplify the f of n as negative x squared y squared all over 2 minus 2xy plus c2 in terms of x. We can now equate f from m to the f from n. The next step is to identify the arbitrary constants and start by canceling similar terms to simplify the equation. Now, c1 is equated to the terms on the right, which is actually not there. Thus, c1 is taken as 0. c2, on the other hand, is the terms found on the left side of the equation, and those are x to the fourth power all over 2 plus 3x. The last step is to gather all terms from both f, which are integrated functions of x and y, and this comprises of the cancelled terms earlier. That would be negative x squared y squared all upon 2 minus 2xy, plus c1 which is 0, and c2 taken as x to the fourth power all over 2 plus 3x. So we get x to the fourth power all upon 2 minus x squared y squared all over 2 minus 2xy plus 3x. Thus, the general solution comes out as x to the fourth power all over 2 minus x squared y squared all upon 2 minus 2xy plus 3x is equal to c. The c is the arbitrary constant from integration. If the standard procedure takes you off, there is a shorter method to get to the general solution. With the same example, which we have already proven to be an exact dE, we follow the same procedure of looking for the general solution of the m term, which came out to be f is equal to x to the fourth power all over 2 minus x squared y squared all over 2 minus 2xy plus 3x plus c1 in terms of y. The general solution for the n function is also taken similar with the previous procedure as negative x squared y squared all upon 2 minus 2xy plus c2 in terms of x, and then equate both the f. Now, instead of solving for c1 and c2, just collect all the terms from the equation, that is, x to the fourth power all over 2, and then take the similar terms negative x squared y squared all upon 2 and also negative 2xy. Then lastly, 3x. Both the constants will have to be considered as c onto the other side of the equation. Let's follow the simpler method in solving example 2 with the differential equation 3x times the quantity of xy less 2 times dx plus the quantity of x cubed plus 2y times dy is equal to 0. First, check exactness, so take m as 3x squared y minus 6x, and its partial derivative with respect to y will be as follows. 3x squared y will have 3x squared as constant, and the derivative of y is 1, then negative 6x is considered a constant where the derivative will be simply 0. So the partial derivative of m with respect to y is 3x squared. Now, n, taken as x cubed plus 2y. This will have the derivative of 3x squared for the first term of x cubed, and 2y will be taken as constant, having the derivative of 0. So the partial derivative of n with respect to x is also 3x squared, so the dE is indeed exact. Solve for the general solution of m and n separately. F is the integral of function m, or that is 3x squared y minus 6x, with the derivative of x. 3x squared y from the first term will have 3y considered as constant, and the integral of x squared is x cubed all over 3. The next term, negative 6x, will be integrated as negative 6 times x squared all upon 2. And by simplifying the solution, we get f of m as x cubed y minus 3x squared plus c1 in terms of y. Now solve for the f from n, and that is the quantity of x cubed plus 2y with the derivative of y. Start with the first term. X cubed will be integrated as x cubed multiplied by y, as x cubed is constant. The next term, 2y, will be integrated as 2 times the integral of y, which is y squared all upon 2. And then add the arbitrary constant c2. So we get x cubed y plus y squared plus c2 in terms of x. Then, from f is equal to f, collect all terms whereby constants will be placed on the right side of the equation. And that would be x cubed y from both terms, then negative 3x squared, and then positive y squared, and all of this will be equated to c.